There we go. So I checked a few things. I checked the bandwidth. There's no problem connecting my computer to the router, and there's no problem connecting from the router to the internet. I was able to sustain about 50 megabits per second. And Discord was, at least it was, using about, it's using less than 0.2 megabits per second upstream. So that definitely would not have been the problem. I also checked to make sure that I'm enabling hardware encoding, and that was I'm pretty sure that was enabled. So that wasn't the issue either. So if we are having a similar problem, I did reinstall Discord. So Discord is completely reinstalled. I removed all the local files and reinstalled Discord. So some people said on the internet that might help. So I guess we'll see today whether that's going to help or not. Alright, so there are some text message coming in. The stream looks good. Alright, cool. Thank you. Alright, thank you for confirming. Alright, so here is the solution video. So I made a video earlier today regarding the solution of the negative exponent program. So what you are seeing on Discord, that link will link you to the solution discussion. So I'm not going to talk about it in class. Once you watch the video and you have questions, go ahead and let me know. So instead, our focus is going to be back to memory devices. And this here, okay, on the screen, that's basically your ungraded assignment from yesterday. So I hope you guys at least have a chance to kind of think about this to see what this is going to do. So what I'm going to do now is to illustrate what the circuit would what you can expect in the circuit as we change the input pins and the output pins. So the first few, all the way from the first row all the way to this row here, that's relatively easy. It's only when we get to the last row where we have to kind of actually put in some extra effort to try to understand that one. Alright, so let me draw the circuit first. We got 2 NAND gates, 2 input pins, and then 2 output pins. So the output of the NAND gates connect to the output pins. The input pin, each one connects to one of the input of the 2 NAND gates. And then the output of one NAND gate connects to the input of the other NAND gate, like so. Okay. You are right. It does not show up. It's not lag, it's just not working. Sorry about that. Because my eye was on the tablet itself, so I wasn't paying attention to whether that was working or not. Let me go back to restart it. There we go. Alright, so let me move it into where you can view it. There we go. Thank you for letting me know. Alright, so what I'll do is I'm going to make a copy of this diagram because I know I'm going to need to use it over and over again. So I'm just going to copy it to somewhere else on the screen. So this way, as I create more of these circuits, I can reuse. I can use that as a template to kind of show how the output would change as we specify the input in a particular way. Alright, so let's get back to the fun part. So the fun part, the first one turns out to be kind of fun because if I don't tell you anything ahead of time, when both inputs are just ones, you really don't know what is the output. Okay, so if you think about both inputs are ones. Okay, this is S, this is R, this is Q, and this is NQ. So when both inputs are ones, okay, all that is saying is everything now hinges on excuse me, the output of the NAND gates, right? because when at least when one input of a NAND gate is a 1, then the output of this NAND gate will depend on the other input of the same NAND gate. But that input, if you track it down, is the output of the other NAND gate. So the reasoning is circular. There's no way we actually will be able to tell what is Q and what is NQ. So the correct answer to the initial state, where S and R are both 1s, is we really don't know. Q and NQ are both question marks. Now, one thing you can deduce is if Q is a 1, then NQ is a 0. If Q is a 0, then NQ is going to be a 1. But since we don't know which one is a 1, and basically it's the same thing as saying we don't really quite know what the output is for the entire SR latch. So what are we going to do? Well, actually nothing. Okay, for the initial state, this is all we can claim, is we don't know what the outputs are. So we don't know what is Q, we don't know what is NQ. Yep, basically that's all we can say. Alright, so we're going to transition to the next state where S becomes a 0 and R remains as a 1. So now we have S being a 0. So the first thing that will see this change would be N1 as a NAND gate. And at this point, because at least one input of the NAND gate is becoming a 0, so now we know for sure that the output of this NAND gate is going to be a 1. Now when that is a 1 combined with this 1 over here, now we can also confirm the second NAND gate is going to output a 0. So at this point we can tell that Q is going to be a 1 and NQ is going to be a 0. Alright. I'm looking at the text channel to make sure that there are no questions. And it looks to me that we do not have a question yet. Alright. So now with that out of the way, let's go to the third state, which is 1, 1. So we are basically saying this pin goes from 0 back to a 1. So once again, we have to think about propagation of change. The first gate that will see this change is going to be N1, because the pin that got changed is one of the inputs to this particular NAND gate. So at this point, N2 is still outputting a 0 right there. So this particular input is a 0. But that means at least one input of this NAND gate N1 is a 0, which means the output will maintain to be a 1. And that's the end of the analysis, because if the output of N1 is not changing, then the other NAND gate is not going to change its output either. So it's just maintaining the state of Q being 1 and NQ being 0. Then we move on to this one, where R is changed from a 1 to a 0. So what's going to happen now? Well, we will once again we'll track down the changes. So because this pin is changed, R is changed, so we'll look at the things. Okay, sometimes it's plural, but in this case it's singular. The one thing that is going to see the change immediately, which is this NAND gate N2. So when N2 is seeing at least one of its input being a 0, it's going to change its output from 0 to a 1. That in return is going to change the input to N1, and N1 is now seeing 1 and 1 as its input, so it's going to change its output to a 0. So that means when we change to this particular state for the input, the output would flip. Q is going to become 0, and then NQ is going to become 1. Are we good so far? I hope so. I'm not seeing any text messages on Discord, and I'm not seeing anyone indicating that we are having a lag issue today, so I'm going to assume everything is still good. Alright, so the next one is, what if both inputs become zeros? So now we are looking at this input being a 0. Okay, so that is actually not too hard, okay, because at this point the top NAND gate is going to see one input being 1 And Falling is correct. Both outputs would be ones in this case. So both outputs would become ones. I shouldn't have crossed out the other one because it can maintain its state of 1. So now you go like, okay, so we haven't seen any really tricky cases. But that's because I forgot one thing. I forgot to change both inputs simultaneously to ones. So now this is going to be interesting. Because if I change, so I'm going to use the template that I saved earlier because now it's going to be useful. So we'll go ahead and make a copy of this down here. And then we'll try to analyze what's going to happen in this case. Alright, so initially we got 0, 0 for input and then 1, 1 for output. And we skipped 1, 1 after 1, 0. Yeah, we probably did so. So the 1, 1 is not going to change any of the output. So the output is going to be maintained after the input become 1, 0. As the input goes from 1, 0 to 1, 1, the output is basically maintained. Thank you for reminding me. So basically, the last analysis is going to be having Q being 0 and having NQ being 1. And going from here to here doesn't change the output. But changing from here to here is the interesting part. So the interesting part is, okay, so now we change both inputs from 0 to 1s simultaneously. So this analysis is going to be interesting because both NAND gates are going to see an immediate change. So as far as this particular NAND gate is concerned, it will see both inputs being 1s, and as far as this NAND gate is concerned, it is the same thing. It's going to see both inputs being 1s. So what does that mean? That means after a certain delay, a propagational delay, both NAND gates will change their outputs to zeros at the same time. But that's not the end of the analysis, because remember, the output of each NAND gate becomes the input of the other NAND gate. So the 0 is going back to this NAND gate, which means the N1 as a NAND gate is going to see at least one input being a 0, and after a certain delay, it will change its output to a 1. But the same thing is going to happen to N2, because N2 is also going to see a change of its input pins. One of the input pins is changing to a 0, which also means after a propagational delay, the output is going to change to a 1. So we now go back to the initial state, and you can see how this is going to be cyclic, because this is going back to the initial state where both outputs were 1s, and now we are both inputs are 1s again, which also means it's going to change from 1 to 0, then change back to 1, then change it back to 0, then change back to 1, and it's not going to end. So basically what we have now is an oscillator, which is unintentional. Okay, this is not why we have the Ssr latch, but if you create a circuit like this and you change both inputs from 0s to 1s at exactly the same time, then it is going to oscillate. So are there any questions about this analysis? Alright, not seeing any questions. Okay, if we are not having any questions, then we'll go ahead and move on to the next device, which is called a D flip-flop. So let me see if I can get back to the notes from before. I think it's this one here. There we go. So we are now done with the discussion of the Ssr latch, and moving on to, yeah, go ahead. Yeah, go ahead. Yes. We just did. We just did. That oscillation? Yes. Yep. Yes. Exactly. You're exactly right, because if I just ask you about something that Logisim can answer right away, then I'm not really testing whether you guys are understanding the concept. I'm just asking whether you can replicate the circuit in Logisim and test it in Logisim, which is not the intention of the exam. So the notes, actually, if you go through the notes, if you go through all the analysis of how the circuit changes, especially with section 5, that really explains, how we can manually follow the changes, how we are, following the propagation of changes. So let's do it one step at a time. And we'll start with section 4, which is the description of a normal, quote unquote normal D flip-flop, which is also known as a level sensitive D flip-flop. And I'm hoping some of you, or most of you, have had a chance to put together the circuit based on how it is described. Okay, so so I'm going to put this together, but using the tablet. I'm not using Logisim to put this together because I don't want the simulation. I want to be able to do this by hand. Okay, I want to be able to analyze the circuit by hand. So so we have two input pins, but this time the input pins are no longer labeled S and R. Remember, S is for set, which means turning something into a 1, and R is reset, which is turning something into a 0. So this time we have D, which is data, and then EN, which is enable. So you cannot see me drawing this on the side because I'm doing this on the tablet. Okay, but I'm when I switch to the tablet, you will see the whole circuit. And we still have two output pins, Q and NQ. So I'm going to draw Q and NQ on the tablet. Once again, you cannot see it yet, but when I switch over to the tablet, you will see the actual circuit. And we utilize one Ssr latch in this case. So that's why we talk about Ssr latch first, because the Ssr latch is the basic mechanism of a D flip-flop. So so I'm drawing a Ssr latch here. You cannot see it just yet, but I'm going to show you when this is all done. The Q pin of the Ssr latch is connected to the output pin of Q. We know that because we see how the Q output is connected to the Q output pin. So those two are connected. And then same thing with NQ. NQ, as the output of the Ssr latch, connects to the pin, which is also named NQ in this case. So the tricky part is, how do we utilize D and EN? So D is connected to the first input of N1, which is a NAND gate. It is also connected to the input of the NOT gate, which is N. Alright, so I'm going to draw this on the tablet. Okay. And then the NOT gate, so let me track down where the NOT gate is connected to. So the NOT gate is connected to the second input pin of N2. Oops, I just oh, that's still not good. There we go. Okay. Alright, so now we have EN. EN is going to the second input pin of N1. And it's also going to the first input of the second NAND gate. Alright. And then we look at the Ssr latch. The output of N1 goes to S, and then the output of the N2 goes to R. So we got N1, N2, this is N. I'm just talking to myself here. This is the Ssr latch. Alright, so I got the circuit created, and I'm going to switch over to the diagram, which is on the tablet right now. There we go. Alright. So when you look at this circuit, okay, it has an Ssr latch as one of the components, and then it has two NAND gates, N1 and N2, and a NOT gate, which is just N, and the data pin is connected to the input of the NOT gate, and then the output of the NOT gate connects to one of the input pins of N2. Alright, so we'll see what's going to happen here. Okay, so the first analysis is, what if En is a 0? Okay, so we're going to say, what if En is a 0? Now we want to analyze the circuit. And En in this case, it's connected to both N1 and N2 directly. So the way we analyze the circuit, okay, I think this is probably a better way to explain it. So we can look at this as a tree. Okay, so En is the root of the tree, or this is the beginning point. This is the starting point of all the changes. So En is being 0. So now, it might be 0 before, but we are making sure that it is now a 0. So the question is, what is it going to affect? So we know this 0 is going to N2. We also know it's going to N1. So this is going to result in N1.out being a 1. It is also going to result in N2.out being a 1. It does not even matter what D is, because in both cases, in both the cases of N1 and N2, if at least one input is a 0, the output is going to be a 1. So this guarantees that both N1 and N2 are both going to output 1, regardless of what the D pin is what the value of the D pin is. So when you combine these two, you can see how both of these are going to the Ssr latch. So as far as the Ssr latch is concerned, okay, so we combine these two. So the Ssr latch is really just keeping its output state, which we do not know, okay, because I didn't tell you what the Ssr latch is outputting. So at this point, we'll just say, Q is unknown, and NQ is also unknown at this point. So do we have any questions about this analysis here? Why, if we know that En is a 0, we just know that whatever the Ssr latch is outputting is just being maintained. And this is regardless of what D is doing. Alright, so the Ssr latch has both of its inputs coming from N1 and N2. N1 goes to the S pin, N2 goes to the R pin. And in the previous analysis, we know that when both inputs of an Ssr latch are 1s, the Ssr latch is just maintaining its current state. And since I did not tell you whether the current state is having Q being 1 or 0, we cannot really know what is the output pin Q or NQ, because all this configuration, SEN being a 0, is maintaining the current state of the Ssr latch. It is not going to change it, but since I didn't tell you what the Ssr latch, what is the current state of the Ssr latch before we turn En into a 0, so we cannot really tell what the Ssr latch is outputting at this point. Does that work? Alright, sure. Alright, so now we're going to do one thing. So we're going to say, okay, let's make D something, okay? So the next analysis is to say, let's make D equal to, let's say, 1, okay? So D turning into a 1 means N1 is going to be affected first. However, because as far as N1 is concerned, one of its input connects to En, and that is still 0 because I haven't changed En yet. So that means nothing is going to happen to the output of N1. And the same analysis also works for N2, because N2 has one of its inputs connected to En, and En is still 0 at this point. So even though D is now a 1, which means the output of this NOT gate is a 0, that is not going to change the output of N2. N2 is going to maintain its output as 1. So basically this means there's no change. Okay, it leads to no changes whatsoever. All right. So now the next thing is, what if we turn En to a 1 at this point? Okay, so now we turn En into a 1, and once again we have to look at the gates that are directly connected to En. So there are 2 of them. Okay, so we'll analyze N1 first. So we'll analyze N1. So En is now not a 0, instead it is a 1. So N1 is gonna say, I can see my first input, D, is maintaining its state of 1, and then I can see the other one, which is En, has now changed from a 0 to a 1. So as far as N1 is concerned, both inputs, all of its inputs are now 1s, which means the output of N1 is going to become a 0. So this is leading to N1.out becoming a 0. Now, that might do something with the Ssr latch, but we are not gonna do that yet, okay? Because we have to follow all the gates that are directly connected to En. Then we go to the next stage, okay? So the other one is N2. Oops, I said N2, but I wrote down N1. So let's go ahead and change that. So now we look at N2, and we go like, okay, how is this going to impact N2? So this is N2 right here. We know En is a 1 already. So when one input of a 2-input NAND gate is a 1, then the output depends on the other pin. So we have to look at this pin here. D is 1, which means the output of the NOT gate is going to be a 0. So as far as N2 is concerned, its output is maintaining to be a 1. So N2.out is continuing to be a 1. In other words, it's not changed. Okay. So both of these pins are going into the Ssr latch. So the next stage of analysis is going to be the Ssr latch. Okay. So now we look at the Ssr latch. So as far as the Ssr latch is concerned, the input pin S is a 0, and then the input pin R is a 1. So from the analysis that we have done yesterday, we know that is going to cause the Ssr latch to change Q to a 1 and NQ to a 0. So this is going to lead to the Ssr latch changing its output Q to a 1 for sure, and it's going to change NQ to a 0 for sure. So are we okay with this analysis? Alright, so we got a thumbs up. Alright. So we're going to do one more, change just to see whether we can follow the propagation of changes. Let's change D from a 1 to a 0 right now. So En is still a 1, but we are changing D from a 1 to a 0. So we want to see what happens in this case. So now we have D changing from a 1 to a 0. So now we want to see how it is affecting something in the circuit. So D connects to both N1 and N2. So once again, we have to split into the analysis of N1 and also the analysis of N2. So as far as N1 is concerned, now at least one input is a 0. So that's going to cause the output of N1 to become a 1 in this case. So this is becoming a 1. And then now we look at N2. So if you look at N2, one of its input pin connects to En, which is still a 1. The other input of N2 is connected to the negation gate, which is getting its input from D. Since D is a 0 at this point, so that means the output of the negation or the NOT gate is going to be a 1. So N2 is now seeing both inputs being a 1, which also means it's going to change its output to a 0. And these changes will go into the Ssr latch. So the next component that we need to analyze would be the Ssr latch. So the Ssr latch is now experiencing a 1 for the S pin and is experiencing a 0 for the R pin. From the analysis of the Ssr latch that we did yesterday, this input configuration will change the Q pin to a 0 and the NQ pin to become a 1. So this is going to cause Q to become a 0, and it's going to cause NQ to become a 1. So at this point, okay, if you have been following along, and if you take a step back, you will basically see that when the EN is a 1, then whatever the D pin is, okay, is going to be mirrored to the Q pin of the Ssr latch. In other words, let me say that one more time. As long as the EN pin is a 1, the R pin of the Ssr latch is going to mirror the state of the D input pin. If D becomes a 0, Q is going to become 0. If D becomes a 1, then Q becomes a 1. On the other hand, if EN is a 0, then whatever D is not going to change the configuration of the Ssr latch, because when EN is a 0, N1 and N2 are both going to output 1s, but when an Ssr latch is seeing 1s for its inputs, it will just simply maintain its current state. It's not going to change Q or NQ to a different state. So are we good with this analysis? In terms of a D flip-flop. And the D of the D flip-flop, that D is data. Because this configuration allows us to use one single pin to specify how we want to change the memory device, and then the other pin to control whether we want to change the device or not, to change the state of the device or not. The Ssr latch is a little bit awkward because one input pin says, hey, if you want to set the Q pin to a 1, turn this wire to a 0. On the other hand, if you want to turn Q into 0, then put a 0 over here. That's kind of awkward, okay? The D flip-flop is a little bit less awkward by saying, how do you want to change the state? Are we going to change it now? So that's why we have D and EN for the D flip-flop. Are we still doing okay so far with section 4, which is the analysis of the D flip-flop device? Okay, I'm not seeing any questions in the text channel, so I'm gonna assume everything is still okay. Alright, so let's move on to section 5. So section 5 is where the analysis of the propagation of changes becomes a little bit more interesting. So let's move on to section 5. And the circuit gets a little bit more complicated too. This is one way to express it. There are other ways to express the same circuit. So let's go ahead and just kind of draw the circuit here. So the first thing is to analyze what are our input pins. There are two input pins. One is CLK, which is the abbreviation of clock, and then the other one is data. The output pin is one single Q output pin. So as far as input and output is concerned, it is no more complicated, in fact a little bit less complicated compared to the previous circuit. We got clock, and then we got data. So data is basically just D, okay, in the previous circuit. It's doing exactly the same thing. And then the output is a single Q as an output pin. The interconnection inside is what is making this circuit a little bit more interesting. So when I draw a circuit, I can either go from the input pin to the output pin, or I can go from the output pin back to the input pin. So let's do it backwards. So let's track down what is outputting what is connected to the output pin of Q. So we can see from here, C, which is one of our Ssr latches, the Q pin of the CSR latch connects to the output pin of Q. So I'm going to draw that on the circuit right now. And once again, you cannot see it just yet because I am still in the process of drawing this. Okay. Alright, so now the question is, what connects to the inputs of the CSR latch? So there are two inputs to the CSR latch. One is S and one is R. So these two nodes connect to the inputs of the CSR latch. So we can see how it is coming out of N1 as a NAND gate. So N1 is special as a NAND gate because it has got 3 input pins. But for now, all we need to know is the output of N1 connects to C.R. Okay, I'm just drawing this in the circuit. And we'll also track down what else connects to R, C.R. Well, that's also connected to N2. The first input pin of N2 is connected the same way. So I'm going to draw a second NAND gate where the output of N1 connects to the first input pin of N2. Okay, there we go. Okay, so that's for C.R. Now we track down what is C.S. So C.S is getting the output NQ from the Ssr latch. Okay, so now we draw the second SR latch, which is labeled S, and then the NQ of the Ssr latch connects to pin S of the CSR latch. And then it also connects to the input, the first input pin of N1. Okay, so we tap it here. Yes, I know I'm just talking to myself, because you cannot see what I'm drawing. I can show you. I mean, it's intermediate. It's not quite done yet. So that's what I have been drawing up to this point. Alright, so I'm just checking, making sure that both of the nodes are done correctly. And now we can move our tracking backwards. So we are now done with so let's track down the Ssr latch. So the Ssr latch has its input connected to these 2 pins, and then S.C is not used. Okay, that's fine. So now we track down N2.out and connect that to S.S. Alright, so this is not gonna look nice because I'm gonna have to wrap around the circuit here. Alright, so I got that. And now we also want that wire or that node to connect to the third input pin of N1. So the third input pin of N1. There we go. Alright. Going back up again. So S.R is connected to the clock pin directly. Alright. There we go. And it's also connected to the second input pin of N1. Alright, so tap here, and then this goes to N1. And now we're going back to, basically there's only one connection left, which is this particular node. All it does is to connect the data pin, which is one of the input pins, to the second input pin of N2. So there we go. This is the super duper easy one. Alright, so I'm done with the circuit now. It looks really ugly, by the way. This is what it looks like. Yeah, I know it doesn't look very nice. I can at least make the input pins closer to the circuit. The top one is the clock pin. The bottom one is the data pin. There we go. So now the question is, how do we analyze this circuit here? Because it has quite a few, kind of feedback kind of mechanism. Because we can see how the output of this N1 kind of wraps around to become the input of this N2 over here. We can also see that this Ssr Latch S is also, its output is also going back to this N1 gate here. And then the output of this N2 is going all the way around to become the input of this Ssr Latch. So the way we analyze this circuit is actually no different from what we have done before. Okay, so we'll go ahead and make certain assumptions. So we'll basically say we do not know exactly what the Ssr latches S and C are doing right now, so we don't know their states. Okay, we don't know whether S.Q is a 1, we don't know whether S.NQ is a 0, and so on and so forth. So we are not making any assumptions. But we have to start the analysis somewhere. So we'll go ahead and say, let's make CLK equal to 0 and see what's going to happen here. So I'm going to change the notation a little bit here. Changing it to 0, I'm going to use an arrow to say that we are changing it. So now what do? Well, we look at the circuit diagram and then we try to track down where that pin is connected to, because those components are going to be directly changed by the change of the clock pin. So we can see that it goes to two components. The first one is the Ssr latch, and then the second one is N1 as a NAND gate. Alright, so the first thing is, now we look at the Ssr latch S, okay, and we ask, well, what can we tell when the clock is going to 0? Well, we know one thing, okay, if the S input of an Ssr latch becomes a 0, we know Q is going to become a 1. So now we know S.Q is going to become a 1, but we are not really sure about NQ, okay, because if all we know is the S input of an Ssr latch changing to a 0, but we don't know what the R input is, we cannot say anything about the NQ pin. All we can say is S.Q is becoming a 1. Okay, so that's basically all we can do with the Ssr Latch S, at least at this point. S.R and not S.S. Oh, right. Okay. Thank you. So NQ becomes a 1, and we have no idea what Q is doing. Thank you. Yep, you're both correct. Paul and Janelle, you're both correct. Good job. Alright. You can see that sometimes I misread my own diagram because I drew the diagram and yet I thought that it led to another input. Okay, so we now look at N1. N1 is a NAND gate and clock is a 0, so that means the output of N1 is guaranteed to be a 1. So that concludes the first stage of propagation changes. Okay, now we look at what S.NQ is connected to, and we look at what N1 is connected to. In other words, we know the after a certain delay, S.NQ is going to change to a 1, and after this about the same kind of delay, N1.out is going to change to a 1. So now we have to ask the question of, well, how will those changes affect the circuit? Now in this case, NQ of S connects to the S pin of C. The output of N1 connects to the R pin of C. So that's convenient because they are converging to exactly the same component. So they are as far as the propagation of changes goes, they're converging. Now we have to look at the Ssr Latch C, and see if we can say anything. Well, turns out we cannot say anything, right? Because at this point we know C.S is a 1, C.R is also a 1 because S connects to NQ of S, R connects to the output of N1, and both of those are 1s at this point. So because the input pins of the Ssr latch C are both 1s, all we can say is it is maintaining its state. Okay, so all we can say is C maintains its state. What state are we talking about? Is Q a 1? Is Q a 0? We have no idea. If I don't tell you ahead of time, you cannot make any assumptions whatsoever. So that would be the full analysis of what happens when CLK, when the clock pin becomes 0. Alright, so now we can make another change. Okay, so let's say the data pin becomes a 1 at this point. So we want to track down, how is that going to change the circuit? So now we are looking at the data pin, becoming a 1, and that 1 is going to go to N2. So now we can say potentially it's going to do something to N2. Now we have to look at the other input pin of N2, because the other input pin of N2 is coming out of N1, and from the previous analysis, N1.out is a 1, so we know this wire has been a 1 before the transition of data becoming a 1. Now that data is becoming a 1, this N2 NAND gate is going to see both inputs being 1s, which means its output is going to become a 0. Since N2 is changing, that means we have to follow the output of N2 and see what else it is going to affect. Now this time is kind of interesting because it is going to 2 different components. The first component that it goes to is N1, and the second component that it goes to is Ssr Latch S. So there are potentially two components that N2.out becoming a 0 can affect. So we'll analyze these one at a time. N1 is right here, and from before, the clock is still a 0 because we are not changing the clock. So one of the input of N1 is still a 0, which means the output of N1 is going to maintain as a 0. So we're going to say N1.out is maintaining a 0. I'm going to use an equal symbol here to basically emphasize that it is not changing to a 1, it is just maintaining. Now if it's maintaining a 0, that means we don't have to follow after N1.out anymore because it is not changing. It maintains as a 1, yes. N1.out is being maintained as a 1. What about the Ssr Latch S? Well, let's take a look. So N2.out, okay, is connected to the Ssr pin, the Ssr Latch S pin, and it's becoming a 0. So we know S.S is changing to a 0, and that means Q is going to become, so this is going to lead to S.Q becoming a 1. So the question is, what about NQ? Is this going to do any changes to NQ in this case? The answer is no, it is not going to do anything to NQ because NQ, it's not going to do anything to NQ because the R pin of this Ssr latch is connected to the clock pin. The clock pin is still a 0. We haven't changed it yet. So the output of NQ of this Ssr latch S is maintaining as a 0. Oops, I said it wrong. It is maintaining to be a 1. The Q pin, is becoming a 1, but it's not really important because the Q pin of this particular Ssr latch is not connected to anything. Nobody cares about the output Q of Ssr Latch S. So this now concludes the analysis of what happens when the data pin becomes a 1 with the clock pin being a 0 already. All right, so do we have any questions at this point? Let me check to see if you guys are following or not. Okay, let me just ask you this. What is C.Q? What is the output pin of Q of Ssr Latch C doing at this point? And I'll even make this a multiple choice. Not change. Okay, so it has not changed. But let me ask you this as a multiple choice question. Option A is 1. Option B is 0. Option C is we don't know. So as far as output pin of Q of the Ssr Latch C is concerned, which is this pin over here, what do we know about that pin at this point? Do we know whether it's a 0? Do we know whether it's a 1? Or do we just know what it is? All right, so the answer is option C. We really don't know what it is, because I never told you about the initial state of the Ssr Latch C, so all we can confirm at this point is it has not changed. So it can be a 0, it can be a 1, we just know that it has been maintained. But which one is it? A 0 or 1? We do not know. All right? Yeah, go ahead. Let me think about that. Well, having a pin change to a 0 does not cause an oscillation. Are you talking about C oscillating? Right, but it has to be simultaneous. So S and R need to become ones at the same time in order to start the oscillation. So they have to be both zeros to begin with, and then switch to ones at the same time in order to start the oscillation. So it's a I suppose that's possible. So you're basically saying, what if N1 and NQ of S are both outputting zeros prior to our confirming the clock becoming a 0? That's what you're asking, right? So I suppose that is possible. So C can be oscillating right now. So we can say C oscillating is its current state, and it's not going to stop the oscillation at this point. It is still one of the possibilities, but the thing is, it can oscillate, and it's going to be okay. Because even if it were oscillating, what we're going to do next is going to stop the oscillation and be able to do something with it. Okay, but you brought up a very good point that C could be oscillating if N1.out was a 0 initially, and then S.NQ was also a 0 initially, and then by changing CLK, the clock pin, to a 0, it's going to cause both S and R of the Ssr latch to become ones at the same time, and that can potentially trigger the Ssr latch to oscillate. That is correct. And it will still be oscillating at this point because we have not touched the C.S and C.R in a way to change its state to one state in specifically. So it would still be, so the statement of the Ssr Latch C is maintained is still kind of valid if you consider oscillation as one of the states. So if it was oscillating before, it will still be oscillating right now. Okay, so the next analysis, the next step is really important. So I'm not going to take row today. So if you're worried about when I'm going to take row, I will just tell you right now that I'm not taking row. I'm hoping that people are not leaving the class like right now. It's like, oh, okay, TAC is not taking row. Let me just go off right now. Okay, because this discussion is actually quite important. So the next one is going to be the clock pin going from a 0 to a 1. And now we want to see what's going to happen, because this really is the crucial step. This is why this circuit is called a clocked or edge-sensitive D flip-flop. Okay, so this is going to be important. So once again, clock goes to two places at the same time. It goes to the Ssr latch. It goes to the N1 NAND gate. So let's see what it's going to do with the Ssr latch at this point. So the Ssr latch, which is this one here, is now going to see the R pin being a 1 instead of a 0. So now we want to know what is the input S doing right now at this point. So from before, we can see that it was a 0. So as far as the Ssr latch is concerned, we know that S.S is a 0. We now know that S.R is becoming a 1. So now we can now confirm the actual output state of the Ssr latch, because both of these conditions is now going to say the output Q is going to be a 1. So I'm not going to use an equal symbol because it is going to become a 1. Okay, if it was not a 1 before, and the S.NQ is going to become a 0 if it wasn't a 0 before. What about N1? So let's take a look at N1. So N1 is this component here. The middle pin is now changing from a 0 to a 1. But in order to understand what N1 is going to output, we also need to know what the other two pins are doing. So this is where things get a little bit interesting, because what about this NQ here? We do not need to worry about NQ becoming a 0, because at the time when we analyze what N1 is going to do at this point, this is prior to NQ of S becoming a 0. So what we need to do is to figure out what is S.NQ doing from before. So S.NQ was a 0 before from here. So now we know the first input pin of N1 is still a 1, because the change of the Ssr latch has not happened yet. Okay, at this time it is starting the propagation, but it has not changed the output of the Ssr latch at this point, because we are still talking about this time here. What about the middle pin? The middle pin connects to the clock pin, which is becoming a 1. So we know both the first and the second pin of N1 are 1s now. So now we only got one more pin to analyze, which is the output of N2. So when you look up output of N2, it is still a 0. So that means N1 dot out is maintaining its output of a 1. In other words, there's no change of the output of the NAND gate N1. Does that mean we are done with the analysis? Not really, because we know the Ssr latch has changed its output. So now we need to know where this N1 is going to, or where this NQ is going to. It's going to two components, and this is where the loop back thing is going to be a little bit interesting, because the output of NQ, this one here, is going to C.S. It is also going back to N1 dot in bracket 1, which is basically the second input pin of N1. So now we have to see what is this going to do to the Csr latch. Okay, the Csr latch is going to respond to the S pin being a 0. So this is this becoming a 0 is going to cause C dot Q to become a 1. Okay? But we also have to follow through and understand what about N1, because N1 is also getting one of its input pins, seeing a change. So is N1 going to do something differently now? So let's go back to N1. The middle pin has changed, but the 0 coming out of N2 is still a 0 at this point. So that means N1 is going to maintain its output to be a 1, which means we are not changing the output of N1. It is just maintaining a 1 at this point. Now, are we done with this analysis? Because one thing got changed, because C.Q is now confirmed to be a 1, which is a change. But are we done with this change? The answer is yes, we are done. Because C.Q does not connect to anything else within the same circuit. So that means once we have hit this particular thing, we now have hit a dead end as far as the propagational changes are concerned. Alright. I'm just looking at the time here. It's 6:30 right now. We still got about 20 more minutes to go. So now what we want to do is to say, let's change the data pin. Okay, the clock pin is now a 1. We'll go ahead and change the data pin and see, oh, okay, what about N1.out? N1.out maintains as a 1 because N2.out is still a 0 at this point. Let me see whether that is true or not. Okay, so that's a good question. And what? Oh, okay. Okay, so Fooling is correct. Okay, we are not quite done yet, because at this point of time, N2 is outputting Alright, so N1 was outputting a 1 before. NQ, this is now a 0, so N1 is continuing to output a 1. But NQ becomes a 0. Right, so because NQ is becoming a 0, so that means at least one input of N1 is a 0. So N1 is going to maintain to output a 1 because let me just put it here so it's clear. So because the first input of N1 is still a 0 at this point because it's coming from NQ. Is that okay? Is that convincing you, Fooling, that N1.out is still maintaining a 0, maintaining a 1 at this point? It is not changing. Okay. Very good. Whew. Okay, so tracking these states, can take a little bit of work. Okay. All right. So now we want to say, well, according to the previous design, as long as the enable pin is a 1, if we change the data pin, the output of the entire device is going to change. So now we want to do something like that, right? So we're going to say, okay, now we have changed our mind, and we have now changed the data pin from a 1 to a 0. So we want to see what the circuit is going to do when we change the data input pin to a 0, now that the clock pin is a 1. So let's go ahead and see what it's going to do here. The data pin is going to N2. So this is directly changing N2 dot in bracket 1. The second input is becoming a 0, and that in return is going to change the output of N2 from a 0, which is from all the way from here, to a 1. So that's going to change N2.out to a 1. Alright, so because N2.out is becoming a 1, that can change two things. That can change N1. It can also change the Ssr Latch S. So now we branch it out and go like, the component S can be changed, the component N1 can also be changed. So now we start with the Ssr Latch S and see whether it's going to do anything. So as far as the Ssr Latch S is concerned, S dot S is now a 1. And we want to know what is S dot R at this point. So we go back and track down S dot R. S dot R has been a 1 already before. So S dot S is becoming a 1. S dot R is already a 1. And together, this means Ssr Latch S is just maintaining its current state, which also means the output of the Ssr Latch is not going to change. So now this is basically a dead end. But we also want to know what is going to happen to N1. Okay. So as far as N1, which is this guy, is concerned, the last input is now a 1. The clock pin is also a 1. And we want to know what is S.NQ. S.NQ has been... What? Was that a question for me? Okay. All right. Yeah, because the voice is kind of choppy on my side, so I couldn't quite tell whether it was talking to me, the voice was talking to me or not. All right. So getting back to N1, right? So N1 has 3 inputs, but the output of S.NQ, which was changed at this point to a 0, it was never changed, by any other, transitions. So because of that, even though N1 dot in bracket, what was it, 2 is becoming a 1, but we also know that N1 dot in bracket 0, which is the first input pin, that is maintaining a 0, and together this means N1 dot out is maintaining its current output of 1, because that's what it was before, and it is continuing to be a 1. So because at this point we have the Ssr Latch as maintaining its current state, there's no further changes, and we also know that N1.out is maintaining its output of 1 and no further changes. So that means as far as the propagation of changes is concerned, we have already hit a dead end. So the data pin going from 1 to 0 is not changing the Ssr Latch C at all. So that means once we have gone through the transition of the clock going from 0 to 1, we can change the data pin and it's not going to do a single thing. Now, you can also say, what if we change the data pin back from 0 back to a 1? Go through the same analysis, and then you will see that, nope, it's not going to change the Ssr Latch. What if I have a falling edge? What if the clock pin is to go from a 1 back to a 0? I can guarantee you there will be no change to the output of the Ssr Latch. And when the clock pin is a 0, you can change the data pin all you want, and it's not going to do a single thing. So the edge-sensitive D flip-flop is special in the sense that the Q pin of the overall circuit is going to mirror the data pin only at the instant when the clock pin goes from 0 to 1. We call that a rising edge. So when the clock pin has a rising edge, right at that moment, the Q pin will follow or mirror the data pin. But at all other time, okay, if the clock pin is a 0, the data pin doesn't change the Q pin. If the clock pin is stable as 1, the data pin is not going to change the Q pin. When the clock pin has a falling edge, going from 1 back to a 0, it is still not going. The data pin is still not going to affect the Q pin. Okay, so this is the special aspect of a edge-sensitive D flip-flop, is it can control the timing when is the Q pin of the design going to be updated, and it's going to be a very short instant of time in this case. Alright, so I'm gonna pause here and see if you guys have any questions about not only the design of the edge sensitive D flip-flop, but also about the analysis of how we follow the changes. The notes, the module, actually contains the text representation of the same kind of propagational change. The changes of the pins are a little bit different, but the analysis is very much the same. So the approach is the same. It's just that the given state, the start state, and what we do after that is different. But you should be able to read the module and follow the reasoning of how the changes propagate throughout the components of an edge sensitive D flip-flop. Alrighty. Any questions? Alright, so assuming that there are no questions, I have a question. So why do we have these two types of mechanisms? The enable is saying, can I change? And then the clock pin is saying, when do I change? So why do we need both? That's kind of the question. So the next design, as if this design is not fun enough, the next one is the next one is a clocked and gated D flip-flop. So in this case, we have 3 input pins. You can see that EN is coming back, clock is coming back, and data is coming back. So this one has both the aspects of EN, which is the enable, and also the clock, which controls when the rising edge might happen, and the data pin, which is how we want to change the Q pin. So now the question is, why do we need both? Okay, isn't one of them already enough, to control when we are going to update the Q pin of the entire design? So without tracking down the transitions and changes and stuff like that, let's focus on what these input pins are, why they are here. Okay. So let me think of it. Okay, so this is a good example. So think about an orchestra. Okay, think about you're going to a concert and there is an orchestra performing at the concert, and here is the conductor. Okay, so the conductor is providing 2 things. Okay, so let's just say that the orchestra is kind of green. People are new to this, and they don't quite know when to play softly and when to get it play a little bit louder, and they cannot keep their own tempo either. So the conductor is doing 2 things at the same time. So the conductor would use his baton. Okay, the waving of the baton, it provides timing. Okay, in other words, it synchronizes the entire orchestra. All the instruments within the orchestra now have the same common time base. That is what the clock pin is about. Okay, the clock pin controls the timing. But who is going to do something? Okay, so even though all of the components inside the processor can now say, okay, now we all understand the clocks, like tick, 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 tick. Okay, but who is supposed to update at that time? That is controlled by EN. That's basically the conductor, looking, staring, giving the death stare at a particular section of the orchestra. Is like, you guys need to get it softer, softer, softer. Okay, but the conductor is still at the same time waving the baton to provide the time basis. Okay, so that is what EN is. Okay, the EN is about the conductor staring at a section of the orchestra to say, you guys need to go softer or louder. Okay, giving command or giving instruction to a specific section of the orchestra. the clock pin, the CLK pin, is about timing. So that is basically about the conductor waving, his or her baton, so that the entire orchestra understand the timing. When is beat 1, when is beat 2, when is beat 3, back to beat 1, and so on. So that's the best analogy I can come up with, to explain why we have a clock pin and also an EN pin at the same time. When we get to the actual circuit of the processor that we'll be using next week all the way to the end of this session, it will be much more clear why we have both. Okay, because of the way the components are connected. They all get the same clock to control the timing, but which one gets to update is up to the EN pin. So that's, when we get to that diagram, I think it will be more clear. I'm looking at the time. We got 5 more minutes, so we'll go ahead and look at this kind of more insane version. So this one has got a reset pin. So the only difference between section 7 and section 6 is the ability to reset a device, reset a D flip-flop to a default state. Okay. So to understand what this one is doing, we have to look at the differences between section 6 and section 7. So I'm going to go back and forth a little bit. This is section 6, and the focus is the SR latch called SRC connecting to the Q pin, and how SR1, the output NQ, is going into the S pin of SRC. /Q is also basically not Q, because in engineering, in electrical engineering, a lot of times they use a slash symbol to mean negation. So when you compare the diagram of section 6 to the diagram of section 7, for the most part they are the same, except the output of NQ from SR1 is now going through a funny looking OR gate before it reached the S pin of SRC, and likewise the output Q from SR2 is now not connected straight to the R pin of SRC. It's going through the AND gate A3 before it gets to the R pin. So now you have to ask the question, what is the reset pin going to do to the SR latch SRC? So that's the question. Okay, let's think about what happens when the reset pin is a 0. Okay, so when reset is 0, then 0 is going to be, this little bubble here means negation, by the way. This bubble here means negation, so the 0 is going to be negated, where O1 is going to output a 1. So when reset pin is a 0, O1 is going to output a 1, which means the S pin is going to be a 1. What about A3? When the reset pin is a 0, it goes straight into A3. A3 is not a NAND gate, it is just a regular AND gate, which means if at least one input is a 0, the output is going to be a 0. So if we know the reset pin is a 0, that guarantees O1 to output a 1. It also guarantees A3 to output a 0. So as far as SRC is concerned, the S pin is a 1, the R pin is a 0. From the analysis from yesterday, we now know that that will guarantee SRC to change its output Q to be a 0, and then not Q to be a 1, but not Q is not even brought out to an output pin, so we don't really care. But we know that the output is going to be, the output Q is going to be a 0. So the reset pin bypasses the clock, enable, and data pin, and it just goes ahead to change the D flip-flop to a default state of 0. So when reset becomes a 0, the output becomes a 0 right away. Doesn't wait for a rising edge of the clock, doesn't care whether the enable pin is a 1 or 0, it just does it. Alright, so now the question is, why do we need the reset pin? As a computer starts up, the transistors are in various states, so that's why we don't know the actual current state of an SR latch when you power up a circuit, because it could be a 1, Q can be a 1, can be a 0, and then depending on the S and the R pin, like what we analyzed a little bit earlier, an Ssr latch can start up oscillating, just flipping and flopping between zeros and ones. That's okay, because now we know we have a mechanism to a reset pin, so that we can now say, regardless of what is the initial state, when we power up, as soon as this reset pin turns 0, the Ssr latch SRC is going to turn to 0 as well. So this is what we call an asynchronous way to reset a D flip-flop. It just bypasses the normal mechanism of how to update the Ssr latch, and we just go like, nope, we're just going to turn it to a 0. When a computer starts up, there's a special circuitry inside basically every single computer that will assert the reset pin to stay as a 0 for a fairly long amount of time, in milliseconds. So what that reset pin is doing is it's going to every single component inside the computer, and so that every single component will receive the reset pin and understand that, okay, I need to reset to the default state of this particular device. That is why your computer always starts at location 0 when it wakes up, when it gets powered up the first time, because the reset pin is asserted before we release the reset pin and go like, okay, now go do your stuff. Okay, but that's after we have reset all the registers. We'll talk about register in the next slide. After all the registers reset to 0. So the reset pin is very significant, because otherwise you have a computer, you have a processor, when you start it up, you have no idea what state it's going to be in. Alright, so this is the last slide, and we are out of time. Okay, so this particular slide is really just replicating this circuit here just 8 times. Okay, so each one of these boxes is the same as this particular circuit here, but the important part is how they are connected. So you can see there's only one single clock pin of the entire circuit, and it is multi-dropped into the clock pin of all of these D flip-flops. There's only one EN pin, and once again the EN pin is multi-dropped into every single one of these D flip-flops. There's also just one single reset pin. Okay, same idea, it is multi-dropped into all of these individual D flip-flops. So now the question is, what is not multi-dropped? What is not multi-dropped is the data pin. This is an 8-bit data pin. It goes through a splitter. Bit 0 goes to one D flip-flop, output 1 goes to another D flip-flop, and so on. So every D flip-flop is receiving a different D bit coming from the input pin D. The output pin Q is also going through a merger, so that the each one of these D flip-flop is contributing to a bit of the output pin, which is also 8-bit wide, that we call Q. So the idea is, when we update 8 bits at the same time. When we output 8 bits. When we reset, we reset 8 bits. But the 8 bits will be updated at the same time, which is controlled by the clock signal. And whether they can update or not will be controlled by the same enable pin. In other words, we're just bundling things together, okay, so that we can say, okay, this entire byte is going to update when the clock goes from 0 to 1. This entire byte is going to update when this EN pin is a 1. So we are just bundling all the bits together, because what can you do with 1 bit, right? Not a whole lot. Okay, with 8 bits, at least you can represent certain values. Okay, you can unsigned, it is going from 0 to 255, and in signed, it goes from negative 128 to positive 127. So a register is really just a combination of D flip-flops. And registers are super important, because they are some of the most useful components, or the most significant components inside a processor. So that's basically what this module is all about. Okay, it basically gets to the point. The conclusion is, this is how we make quote-unquote registers inside a processor. And how we use registers inside the processor, that we'll explain tomorrow and the day after. Alright, so I'm done with this module, which means we are going to move forward to the next few slides, which is kind of confusing. Let me just explain why that part is confusing before I end today's lecture. It's confusing because, okay, let me see what this is. I think that's the test. Yep. Because at this point, I am not going to rely on my own notes anymore. And if you have been following the topics in Canvas, so the next thing that we're going to talk about is a clocked circuit. But we are also going to talk about RAM, ROM, and also multiplexers and demultiplexers. So these are not things that I am writing because they're already built into LogiSim. So we'll start talking about these tomorrow. Okay, so tomorrow we'll talk about RAM, we'll talk about ROM. We might be able to get to multiplexers and demultiplexers once we have explained these individual components. Then we'll start to look into the TTP architecture, which is the abbreviation of Text Toy Processor. So we'll start to put all the things together so that we can actually start to do some processing. Okay, we can add, we can subtract, we can compare, and so on. So that's the end of today's lecture. There is no new lab tonight because because I released the positive exponent quiz already, lab already, and the solution of the negative exponent lab is already posted in today's lecture. So if you were not with us at that time, I'm going to pin it too. So if you look at the pinned messages of today's text messages, the first one is the link to the synchronous lecture itself. The second one is linked to the solution of the negative exponent homework, which should help you, with doing the positive exponent homework. So I'm just going to leave it at that. The positive exponent homework is due the day after tomorrow. So if you have any questions, you still have one day to ask those questions. But keep in mind that I cannot be watching and answering questions on Discord all day long. I do have office hours from 11 to noon. Other than that, the turnaround time is 24 hours, or the guaranteed turnaround time is 24 hours. But don't count on me, reading my messages at 1 p.m. or 1 a.m. because I actually get messages at 1 a.m. asking me questions about the homework assignments. Not going to answer that at 1 a.m. Alrighty, so let me just check the text channel and see if there are new messages. Nope. Okay, so we are good. I'm going to sign off, but I'll be back in about 10 minutes. So if you have any questions about the solution of the negative exponent assignment, or if you have any questions about the positive one, we can talk about that. Alright, so I'll see you guys tomorrow if you are not going to ask questions. Alright, bye.